Okay, in this video I want to give you a little heads up for the exam on homework 6.6 and also help with homework. So this will be a 15-point problem on the exam, but it's also homework problem. So student cycle engine, I call it that because it's probably a cycle that doesn't have a name since it's randomly generated, is analyzed using the cold air standard method. I'm going to define each process with two variables. Here for process 1, 2, the first letter is what is held constant. So this is a constant temperature process or an isothermal process. And then the second variable here, V, is what ratio is given. So I'm going to give a volume ratio. So it will be a isothermal compression with the compression ratio given. The second process is isobaric, constant pressure, also with a volume ratio given or compression ratio given. The third process is a constant volume process or isometric process with a temperature ratio given, followed by another heat addition process, which is constant volume. So constant volume heat addition where the pressure ratio is given. And then finally, to get back to our original state of state 1, it's going to be isentropic expansion. A volume ratio will be given, and then constant volume heat rejection and the temperature ratio will be given. The ratios are all given as the larger value over the smaller, so you will need to know that the first two values are compression processes, so the specific volume will go down. The next two processes are heat addition processes, so the energy will go up. And then the last two processes just get us back to the state. First to the volume of the final state, and then finally to the temperature of the final state. So we can calculate the equation for efficiency just from the values given here, but if we want to actually get a number for the efficiency, then we would need to use the ratio. So this is the ratio for process 1, 2. So this compression ratio is 3.2. The compression ratio for the next process, or VR2, is 2.6. For process 3, 4, the temperature ratio is 3.57, and finally the pressure ratio is 2.74 for the last process where a ratio is given. These two processes don't have a ratio listed because they can be calculated from the given values. So let's take a look at first off what we need to solve this problem. I'm going to write down the general equations at the top, and then we'll kind of work through how to get to this final equation for efficiency. I'm going to move over to the board. So for starters, we probably want to have first law, Q minus W equals delta U technically, but delta U can be written as M CV delta T for constant specific heat, so I'm going to write it that way. M CV delta T, or if it's, say, 1 to 2, then this would be T2 minus T1. Of course, I can use it for any process, but I'll just illustrate it here for process 1 to 2. If Q and W are both non-zero for a process, then we'll need another equation. It'll work for 1 to 2. Could be given as the integral from state 1 to 2 of P dV. And then depending on the process, we get some different results. So we have, if it's P equals constant, get one result. If it's an isothermal process, you get another result. Of course, if V equals constant, kind of get the trivial solution. One more equation I'm going to write up here at the top is that PV equals MRT. So we're assuming constant specific heats, air is an ideal gas, and then making some other assumptions for each process. So let's start with, what if the pressure was constant for some process? Then the pressure could come outside the integral. So I have P integral dV, which gives me from 1 to 2, say P2 V2 minus P1 V1. And if I note up here that PV equals MRT, I'm going to simplify this and replace PV with MR T2, and since T1 is also multiplied by MR, T2 minus T1. So it's MRT2 minus MRT1. Now what if we had a constant temperature process? Well then work equals integral P dV, but pressure I can write as MRT over V, so I'll do the integral of MRT over V dV, and I can bring the M outside the integral, the R outside the integral, and the T outside the integral because it's a constant temperature process. The mass is constant, the gas constant is constant, and so I get equal M R T and then the integral of 1 over V dV. I'm kind of running out of room there, so let me write that below here. Equals MRT integral 1 over V dV, which is MRT1. I can put T2 or T1 since they're the same, natural log of V2 over V1. And then finally, if V equals constant, so this is for constant temperature, and then finally for V equals constant, work equals integral P dV, but V is constant, so there is no dV, so that's 0. And there's one other time we might want to think about the work, which is what if the entropy is constant. And the easiest way to deal with that is, well, if entropy is constant, then Q is 0, so Q minus W equals M CV T2 minus T1 if it's process 1, 2, so that the work equals M CV T1 minus T2. So we've got the work for a constant pressure process, a constant temperature process, a constant volume process, and a constant entropy process. Those are the only processes that we're going to consider for this mystery problem. And we can get a lot of different cycles just with those processes. So I'm going to erase that. Save this though. So we know that we have this equation that we can come up with those 4 situations or those 4 results. And again, you don't really need to memorize them. You just need to know how to integrate PDV and use the ideal gas law to manipulate those. Okay, so let's draw this process out. I'm going to get my sheet where I've kind of worked it out on paper. Okay, so if you look on the problem, it says the first process is TV. So I'm going to do a little PV diagram. And so a constant entropy line, by the way, this is starting at the largest volume, lowest pressure. It's the beginning of the compression process. So an isotropic process looks like that. An isothermal process looks like that. So there's my isothermal process. So my first process is TV, which means it's a constant temperature process with a volume ratio given. So I don't need this line because it's not isotropic. The next process is constant pressure. So here's state 2. So this is a constant pressure process to state 3. So those are my 2 compression processes. And on this one, temperature ratio is given. So you can see here, if I continue this temperature line, this would be a lower temperature line. So the temperature drops in that second process. Then the third process is a constant volume process with a temperature ratio given. So it's a heat addition process, so I'll be going up. This is constant volume and temperature ratio given. Then the next is another constant volume process with a pressure ratio given. So it will continue on up to state 5. Again, constant volume. The next process is a constant entropy process. Now these are the 4 ratios given. And from this point I don't have a ratio, although I could put one here. So I listed one, but we can find it, but these are going to be calculated. So it's an isentropic process, so it's going to be a little steeper than the constant temperature line, and we know that we're going all the way back to the volume of the original state. So we stop when we get to the same volume. And then the final process is a constant volume process, and the temperature ratio is given. So the last state 6 to state 1, the last process is like that, and this is a constant entropy process, constant volume. So it's not that far from being an Otto cycle. It's just got this extra little segment in there with a constant pressure process from 2 to 3. Okay, so let's start by trying to find the temperatures. So T2, that one's easy, it equals T1. T3, I'm given a temperature ratio between T2 and T3, so that one is easy. So here our T1 is going to be the larger over the smaller, so it's going to be T2 over T3. So T3 then would be T2 divided by our T1. Or sorry, that was a put temperature, but it was actually a volume ratio that was given there. So this is V2, and this one I'm going to call our V1. This is actually a volume ratio, which is, if it was a temperature ratio, that would be the way to do it, but this will be V2 is the bigger one over V3. Alright, so let me just come up with the same result, but let's just look at how this is derived. So then I have P3 V3 over P2 V2 equals our T3 over our T2. So R is divided by R is 1. P3 over P2 is 1 because it's a constant pressure process, and V3 over V2 is 1 over my R V2. So I get here that T3 equals T2 times 1 over R V2, which is what I had. So it really, it's a temperature ratio like the same as it is a volume ratio, except it's 1 over. Okay, then I have T4 for the next process. It's temperature ratio that's given, so that's going to be our T1 equals the higher, which would be T4 over T3. So this is just going to be T3 or T1, 1 being the first temperature ratio that I'm using. And then the next process is a pressure ratio given. So T5 equals T4 R P1. That one's a little maybe harder to understand. R P1 equals P5 over P4, and I'm going to write over here P5 over P4 V4 equals R T5 over R T4. And in this case, R's cancel, the V's cancel because it's a constant volume process. And this P5 over P4 is what we're calling RP1, but that's the same as the temperature ratio. So the pressure ratio equals the temperature ratio. So again, it's just times RP1. And then finally, T6 equals T5 times 1 over R to the, well, 1 over the compression ratio to the K minus 1, but let's look at what that is. So this this ratio of V6 over V5, let me write this as the basic equation. So T6 over T5 equals V5 over V6 to the K minus 1. That is the equation for an isentropic process, which 5 to 6 is. So I need to know what is V5 over V6. So V5 over V6, I can replace V5 is the same as V3. It's the same as V4 also. And so this is going to be V3. And V6 is the same as V1. And then if I multiply and divide by V2, or divide both the numerator and denominator by V2, that doesn't change anything. So V2, right? And then V1 over V2 is, in the denominator, is RV1, and V3 over V2 is 1 over RV2. So I have that V5 over V6 equals 1 over RV1 RV2. So now I can write this as T6 equals, sorry, let's write this way, T6 equals T5 times 1 over RV1 RV2 to the K minus 1. Let me just write that not so close to the edge. So finally, T6, T5 divided by RV1, RV2 to the K minus 1. Okay, so now I have all my equations for temperature. The first one's kind of hiding here, T2, then T3, T4, T5, and T6. And I could write them all as functions of T1 if I replace T2 with T1. So this would be T1 over RV2, and this one would be T1 over RV2 times RT1, and so on. I could do that for every term, write them all as a function of T1. And then finally, I need to find the work and heat transfer that's appropriate for each cycle. So I'm going to erase these. I'll keep my temperatures in there on my piece of paper. Okay, so I have that the efficiency equals all the work. So let's look at the positive ones. There's work from 1 to 2, It's negative, but it's work. There's also work from 2 to 3. There's no work from 3 to 4 because the volume's not changing. There's no work from 4 to 5, the volume's not changing. And then there's work from 5 to 6. And then again, no work from 6 to 1 because the volume's not changing. So the first one is negative, the second term's negative, and the last term is only positive work. And then finally we need our Q in. So we have Q in, actually from 1 to 2 we have Q out. From 2 to 3 we have Q out. From 6 to 1 we have Q out. So, but the only Q ins are the Q from 3 to 4 and the Q from 4 to 5. So I can now replace those work terms with the equations for, let me just write them first as each of those. So let's do work 1, 2. And for the first process, it's an isothermal process, so work from 1 to 2 equals integral P dV, which I can replace P with mRT over V dV. And the numerator is constant, so I can bring that out and I get mRT1 natural log of V2 over V1. And V2 over V1 is equal to 1 over RV1. So I have mRT1 natural log 1 over RV1. I then work 2 to 3 equals the integral P dV, but it's constant pressure, so it's P delta V. And I can replace P times V with mRT, so I get mRT3 minus T2. And work 5 to 6. It's an isotropic process, so it's just mCV dt, but I'm going to change it's really negative work equals mCV dt, so mCV, and I'll do the initial minus final, since I'll switch the order of those two terms. So I don't have the negative sign. So I can add these 3 terms together, put them in the numerator, and then Q3, 4. There's no work in that process, so it's just equal to mCV times the temperature difference, which is T4 minus T3, and Q4 to 5 equals mCV T5 minus T4. So now I have all the necessary work and heat transfer. I stick those into the equation for efficiency, and it gets a little messy, but we can do that. So efficiency equals, the first term is my work 1 to 2, which is got an R in it. I also notice I'm going to divide everything by M. And then the M's are all gone. And since every term has been divided by M, those can just cancel out. So it's the same I could do in this efficiency equation. If I divided the numerator and denominator by M, I can do this as work per unit of mass. So I don't need the M's. The other thing I could do is divide every term by CV. If I do that, the CV's will cancel. So if I divide by MCV every term, then that's like dividing all the values in the numerator and all the values in the denominator by CV, which I can do. If I do that, I have an R. This R in the work 1, 2 becomes, it's R equals CP minus CV. So if I divide that by CV, then I get K minus 1. So my R becomes K minus 1. This R becomes K minus 1. And then these CVs cancel out. So I've got no M anymore. And so my first term will be 1 to 2 is T1. Actually, K minus 1, T1. Let's put that first. So K minus 1, T1. Natural log of 1 over RV1. My second term is work 2, 3, which is K minus 1 times T3 minus T2. And my third term is work 5, 6, which is just plus T5 minus T6. And in the denominator, I've got T4 minus T3 and plus T5 minus T4. And then a few things that simplify. Of course, I have plus T4 and minus T4, so those cancel, and I'm just left with T5 minus T3 in the denominator. And might be able to do a few things in the numerator, but I can just leave that alone. If I replace every temperature term with a function of T1, like T2 equals T1, so this is easy. This second term becomes let's see, T3 was T1 over R, or T2 over RV2, which is T1 over RV1, so this term became T1 over RV1, and likewise do that for 5 and T5, T6, and the T5 and T3 in the denominator. I'll have a T1 in every term, and then I can get rid of the T1. And finally, I'm left with only a function of V1, V2, RT, RP, and K. And I'm going to write that out, what I've got for the final solution. And you can try and find that yourself. And if you plug in values, you should get the same answers as I got on the example problem. So finally I get that the efficiency equals K minus 1 over RV2 minus 1 plus K minus 1 natural log. I switched these first two terms, I'm not sure why, but RV1. This last term's a little bit large. Let me, so it's RP RT over RV2, and that's multiplied by 1 minus 1 over RV1, RV2 to the K minus 1. And then divided by 1 over RV2 times RP RT minus 1. So there's no T1 left in that equation, and just a function of, so the efficiency finally is a function of RV1, RV2, RP, Now, for this problem, that might be a lot of work for the exam, especially in 10 or 15 minutes. So I will probably simplify, maybe give you part of a completed problem. Maybe I'll have you start it, maybe finish it, tell me what the work for a process is, what the temperatures are. But make sure that when you come to the exam, you could do an entire problem, especially if it was a simple one. And that's the mystery problem.